Welcome to EDU World Space.
Okay, for this problem, we're considering a heavy particle that is suspended from a string. So that looks something like this, where a particle has some mass m, and they tell us that the length of the string is 1.5 meters. And we give that particle some horizontal velocity, v naught, where V naught is equal to the square root of 57 meters per second. We are additionally told to consider G equal to 10 meters per second squared, and we want to know firstly, at what angle will the line go slack? This is the point where tension in the rope is equal to 0. We want to know in part B, what is the velocity at that point? And in part C, we want to know what is the maximum height that the particle reaches. So sometime later, our picture is going to look different. So let's start by drawing what the new picture looks like. So it tells us to consider theta from the vertical, and I'm going to assume that the particle makes it up here somewhere, but doesn't make it all the way around. And you can check this using conservation of energy. So I did that quickly. I'm not going to go over it here, but if you use conservation of energy, you'll see that the maximum height that this particle can reach, given that initial velocity, is not enough to go all the way around. So that means somewhere up here, the line is going to go slack. Our angle theta that we're interested in knowing is what I just labeled on the graph there. We also are interested in what the velocity is at this point and what is the height. So to start, we need to in some way involve that angle theta in order to try and figure out what theta is equal to. And so my first thought was either conservation of energy or Newton's second law for rotational motion. So this particle is going around in a circle, and we know that the sum of the forces in the radial direction should be equal to mv squared over r. So I'm actually going to start with this equation in order to figure out what the maximum height is. We could also look at conservation of energy as a starting point, but I'm going to choose this as my starting point. And so in order to do this, we of course want to draw a free body diagram. So if this is our particle, we already know that if the string is slack, then the tension force is 0. So the only force acting on this guy is mg downward. But it is moving in circular motion. And so we need to figure out what the radial component of the gravitational force is going to be equal to. Because we know, let me redraw that. Because we know that this angle is theta, that tells us that this angle is also theta, which tells us that this angle is theta. And so when we're considering the component of gravity that is in the radial direction, it's going to be the mg cosine theta component. So now that we've figured that out, that is the left-hand side of the equation here. And all of that has to be equal to mv squared over r. We can, of course, cancel m, and I'm going to replace r with L because that's what I've labeled the length of the string, which would correspond to the radius of the circle. And we have a problem here. Both theta and v are unknowns. They're things that we're trying to find. But the thing I want to find first is theta. So I'm going to start by solving this equation for something in terms of theta. So I can hopefully plug it into something else and end up getting theta out as an answer. So if I do that, then we see that v squared is equal to g times L times the cosine of theta. Now we're going to use conservation of energy. So energy initial has to equal energy final. And again, we could have started with conservation of energy and then did rotational Newton's second law. The order doesn't really matter because we need to use both in order to get to the answer. In our initial picture here, there's only kinetic energy. And that kinetic energy is going to be equal to 1/2 mv naught squared. In our second picture here, we have both kinetic energy and potential energy. So kinetic energy is going to be 1/2 mv squared. And again, we now have something for v squared that we can plug in, plus mgh. And here becomes a little bit of a problem again because we don't know what h is. But if we go back to our diagram, we can again use some helpful angles to figure it out. So again, we know that this angle is theta. That makes this angle theta as well. And so we can break up h into two components. The component from the suspension point to the horizontal, which is going to be of length L, and then the component that is above the horizontal, and that is going to be L cosine theta. And so we can add those together to get h. So h here is actually going to be equal to L plus L cosine theta. Having all of that information, we can now go back to conservation of energy and start plugging things in and trying to solve. So first, I'm going to go ahead and cancel all the masses because mass doesn't matter here. And we again have 1/2 v naught squared equals 1/2 gl cosine theta, because v squared is gl cosine theta, plus, and again here we have g times h, where h is L plus L cosine of theta. And I'm running out of space on the screen here, but we want to go ahead and simplify. I'm going to skip over some of those algebra steps because you should be well versed in algebra, but you're going to do some algebra to solve for cosine of theta. And you should get that cosine of theta is equal to 1/2 v naught squared minus g times L, all divided by 3/2 g times L. Or at least that's the way that I chose to simplify it. And you plug all of that in and you get that cosine of theta is 0.6. Doing inverse cosine, you can get that theta is equal to 53 degrees, because 53 degrees is inverse cosine of 0.6. Then we can go back to this equation here to figure out what v is. So v is going to be the square root of gl cosine of theta. And when you plug all that in, you should get that v is 3 meters per second. And then lastly, h. H, we can go back to here. H is L plus L cosine theta. And when you plug in all of the numbers, you get 2.4 meters for L. Or sorry, for H.